The primary flight control system uses conventional control wheel, column, and pedal inputs from the pilot to electronically command the flight control surfaces. The system provides conventional control feel and pitch responses to speed and trim changes. The system's electronic components provide enhanced handling qualities and reduce pilot workload. The flight control surfaces provide control for pitch, roll, and yaw. Pitch control is provided by 2 elevators and a movable horizontal stabilizer. The elevators and horizontal stabilizer work together to provide pitch control. Roll control is provided by 2 flaperons, 2 ailerons, and 14 spoilers. The flaperons and ailerons provide roll control assisted by asymmetric spoilers. The flaperons are located between the inboard and outboard flaps on both wings. In the normal mode, they are used for roll control with the flaps retracted or extended. The flaperons also droop with the trailing edge flaps to improve slow-speed performance. The ailerons are located outboard of the outboard flaps on each wing. The ailerons and spoilers droop with the trailing edge flaps to improve slow-speed performance. During high-speed flight, the ailerons are locked out since the flaperons and spoilers provide sufficient roll control. During low-speed flight, the ailerons operate to augment roll control. In addition to providing roll control, spoilers are used symmetrically as speed brakes. Yaw control is provided by a single rudder. During takeoff, the rudder becomes aerodynamically effective at approximately 60 knots ground speed. Flaps and slats are used to provide high lift for takeoff, approach, and landing. Review the flight control surface locations before pressing the Continue button to resume the lesson. Individual flight surfaces are controlled by 4 actuator control electronics, or ACEs. The flight control system is powered by the hydraulic system, the electrical system, or the RAT. Review the ACEs and hydraulic power distribution before pressing the Continue button to resume the lesson. In the unlikely event of the loss of all hydraulic power, the electrically actuated stabilizer and 2 spoiler pairs allow pilot control of pitch and roll using the primary pitch trim switches, alternate pitch trim switches, and the control wheel. If there is a complete loss of flight control signaling, direct wiring from the flight deck to the stabilizer and a spoiler pair allow pilot control of pitch using the alternate pitch trim switches and roll using the control wheel. The ICAS caution message, Flight Controls, is displayed if multiple ACE and/or hydraulic system failures cause the loss of a significant number of control surfaces, or other significant flight control system faults are detected. There are 2 flight control surfaces lock switches located on the overhead panel for locking out the flight control surfaces on the tail and wings. The flight control lock switches are for use by maintenance personnel to prevent surface movement when working on or in the area of the control surfaces. When a switch is selected to the lock position, the flight control surfaces on the tail or wings lock in place. And the ICAS advisory message, Flight Control Locked, is displayed. The Flight Control Lock fail light will illuminate when a lock switch is in the lock position and any of the associated surfaces do not lock. In addition, the flight control surfaces automatically unlock when ground speed exceeds 40 knots. The pilot controls consist of 2 control columns, 2 control wheels, 2 pairs of rudder pedals, the speed brake lever, the flap lever, control wheel pitch trim switches, stabilizer cutout switches, rudder trim selector, alternate flap switches, and alternate pitch trim switches. The columns, wheels, and rudder pedals are connected through jam override mechanisms. If a jam occurs in a column, wheel, or in the rudder pedals, the pilots can maintain control by applying force to the other column, wheel, or rudder pedals to overcome the jam. Flight control indications are found on primary ICAS and the flight control synoptic. Review the flight control indications before pressing the Continue button to resume the lesson. There are 3 primary flight control system modes: normal, secondary, and direct. All 3 modes use the same pilot controls and flight control surfaces. During manual flight in normal mode, pilot control inputs are sent to 4 ACEs. The ACEs send these signals to 3 primary flight computers, or PFCs. The PFCs verify the signals and information from other airplane systems to compute enhanced control surface commands. The commands are sent back to the ACEs and subsequently to the flight control surface actuators. During manual flight in normal mode, the primary flight control system provides flight envelope protection. Flight envelope protection reduces the possibility of inadvertently exceeding the flight envelope by providing crew awareness of envelope margins. The flight envelope protection includes the following functions, which will be described in greater detail later in the lesson: bank angle protection, overspeed protection, and stall protection. When the autopilot is engaged, the autopilot system sends control surface commands directly to the PFCs. The PFCs generate control surface commands, which are sent to the ACEs and then to the control surface actuators. The autopilot will backdrive the pilot controls to provide awareness of what the autopilot is doing. If the pilot overrides the autopilot with control inputs, the autopilot disconnects and the flight control system uses the pilot control inputs. After landing, a series of flight control self-tests are run when the flaps and speed brakes are retracted and the ground speed is less than 30 knots. The first series of tests, which take approximately 90 seconds to complete, require hydraulic power to be on. The tests require that hydraulic power not be interrupted and that there be no large-scale flight control inputs. If the engines are shut down before the flaps are retracted, the tests are not accomplished. If the tests are interrupted or are not accomplished on 2 consecutive flights, a fault condition may be set. An additional series of flight control self-tests are run when the first series of tests are complete and all hydraulic systems are depressurized. These tests take approximately 70 seconds and require that hydraulics remain unpowered and the flaps or speed brakes not be moved during the tests. While each series of tests are running, various ICAS alert and status messages display, the trim indication blinks, and various failures display on the flight control's synoptic page. When the self-tests are complete, the ICAS alert and status messages are removed, and the trim indicator and synoptic display return to normal. The PFCs will automatically revert to secondary mode when inertial or air data is insufficient to support normal mode, or when all slat and flap position data is unavailable. When the primary flight control system reverts to the secondary mode, the ICAS caution message, Flight Control Mode, is displayed. In secondary mode, the ACEs continue to receive and process pilot control inputs before sending these signals to the 3 PFCs. The PFCs use simplified computations to generate flight control surface commands. These simplified commands are sent back to the ACEs and then sent to the control surface actuators. All flight control surfaces remain operable. However, the elevator and rudder are more sensitive at some airspeeds, and yaw damping is degraded. In the secondary mode, the following functions are not available: gust suppression, autopilot, auto speed brakes, envelope protection, pitch compensation, roll-yaw asymmetry compensation, and tail strike protection. The ACEs automatically transition to the direct mode when they detect the failure of all 3 PFCs or they lose communication with the PFCs. The direct mode can also be manually selected by moving the primary flight computer's disconnect switch to disconnect. When the system is in the direct mode, the ICAS caution message, Primary Flight Computers, is displayed. In the direct mode, the PFCs no longer generate control surface commands. Pilot inputs received by the ACEs are sent directly to the control surface actuators. The direct mode provides full airplane control for continued safe flight and landing. The airplane handling qualities are almost the same as the secondary mode. All flight control surfaces remain operable, but yaw damping is degraded. In the direct mode, the following functions are not available: gust suppression, autopilot, auto speed brakes, envelope protection, pitch compensation, roll-yaw asymmetry compensation, and tail strike protection. In the normal mode, the airplane pitch control characteristics are similar to conventional airplanes. The control column input commands the PFCs to generate a pitch maneuver where the rate is dependent on column displacement. The PFCs automatically position the elevator and stabilizer to generate the commanded maneuver. The PFCs also constantly monitor airplane response to pilot commands and reposition the elevator and stabilizer accordingly. The PFCs provide pitch compensation by utilizing control surface commands to minimize airplane pitch responses to thrust changes, configuration changes, turbulence, and turns up to 30 degrees of bank. The PFCs automatically control pitch to maintain a relatively constant flight path. This eliminates the need for the pilot to make control column inputs to compensate for these factors. For turns up to 30 degrees of bank, the pilot does not need to add additional column back pressure to maintain altitude. For turns of more than 30 degrees of bank, the pilot does need to add column back pressure. As airspeed changes, the PFCs provide conventional pitch control characteristics by requiring the pilot to make control column inputs or trim changes to maintain a constant flight path. Airplane pitch control in the secondary and direct flight control modes differs from normal mode. The flight control system continues to receive and process pilot control inputs using simplified computations to generate flight control surface commands. Secondary and direct modes do not provide automatic pitch compensation for flap and speed brake configuration changes, gear configuration changes, thrust changes, turns to 30-degree bank angle, or turbulence. Stabilizer position commands are processed through two independent channels within the flight control system. The commands come from the primary or alternate pitch trim switches. The stabilizer is moved using an electric control unit powered by the L2 and R2 AC buses. Stabilizer position is displayed on ICAS and on the flight control synoptic. The indication on the synoptic is constantly displayed. The ICAS indication is displayed on the ground at power-up. The indication is removed when either of the following conditions are satisfied: gear up for 10 seconds or 60 seconds after liftoff. The ICAS stabilizer position indication is automatically displayed after landing if any pair of pitch trim switches are used or ground speed is less than 40 knots. The indication is displayed in the air if any of the following ICAS messages are active: flight control mode, pitch down authority, pitch up authority, primary flight computers, stabilizer, or stabilizer cutout. The green band indicates the allowable takeoff trim range based on gross weight and CG information from the FMC. A default green band is displayed from 4 to 9 units of trim prior to performance data being entered into the FMC. When the green band signal is not present or is invalid, the green band is not displayed. A stabilizer green band monitor helps confirm that the green band is correct based on the gross weight and CG entries in the FMC. Two nose gear pressure transducers provide actual airplane gross weight and CG information. The nose gear pressure data is used to determine two separate sets of validation limits, one for each transducer. The FMC calculated stabilizer green band is then compared to the validation limits from the transducers. The ICAS advisory message, stabilizer green band, is displayed if the computed green band disagrees with pressure transducer data, the two transducer values are not within the set tolerance, or either transducer has failed. If uncommanded stabilizer motion is sensed, the stabilizer channel that caused the motion is automatically shut down. If a channel is inoperative, the ICAS advisory message, stabilizer L2 or stabilizer R2 is displayed. The stabilizer remains operative through the remaining channel. If the affected channel cannot be isolated, both channels are shut down. If both stabilizer channels are inoperative, the ICAS warning message, stabilizer, is displayed. This warning is also displayed if the automatic shutdown fails to stop the uncommanded motion. The L2 and R2 stabilizer cutout switches, located on the aisle stand, control electric power to the independent stabilizer channels. When both switches are placed in the cutout position, all power is removed from the stabilizer, and the ICAS advisory message, stabilizer cutout, is displayed. With both switches in the cutout position, the stabilizer warning message is not displayed. When the stabilizer has failed or is shut down while in the normal mode, pitch trim is still available through the elevators. Pitch trim commands from the primary or alternate pitch trim switches can be used to change the trim reference speed. The elevators will trim the airplane. However, the stabilizer does not move. The column cutout function is designed to stop the effects of uncommanded pitch trim input from jammed or failed pitch trim switches. If a nose-up or nose-down pitch trim command from either the primary or alternate trim switches is opposed by either control column for more than 2 seconds, the column cutout function disables the specific pitch trim switch commands until the switch input indicates no trim input. If the column cutout function remains active for more than 20 seconds, the stabilizer L2-R2 ICAS advisory is displayed. The flight control system reverts to direct mode, and the uncommanded input is removed by system shutdown. Control cutout is deactivated on the ground to allow trimming nose-down stabilizer with aft column input during a touch and go. Primary pitch trim is controlled by the dual pitch trim switches on each control wheel. Both switches must be moved to command trim changes. The primary pitch trim switches are inhibited when the autopilot is engaged. Pitch trim does not move the control column. In the normal mode, primary pitch trim operates differently on the ground than it does in flight. On the ground, using the primary pitch trim switches will move the stabilizer directly. In flight, using the pitch trim switches does not position the stabilizer directly, but will command the PFCs to change the trim reference speed. The trim reference speed is the speed at which the airplane would eventually stabilize if there were no control column inputs. When pilot trim inputs are made, The PFCs automatically move the elevators to achieve the trim change before moving the stabilizer, which streamlines the elevator. Stabilizer motion may also automatically occur to streamline the stabilizer and elevator for thrust and configuration changes. Once the control column forces are trimmed to zero, the airplane maintains a constant speed with no column inputs. Thrust changes result in a relatively constant indicated airspeed, climb or descent, with no trim inputs needed unless airspeed changes. In the secondary or direct modes, primary pitch trim operates the same on the ground and in flight. In both situations, the primary pitch trim switches will directly position the stabilizer. Alternate pitch trim commands have priority over primary pitch trim commands in all flight control modes. Alternate pitch trim is controlled by the dual pitch trim switches located on the control stand. Both switches must be moved to command trim changes. The switches are linked electrically to the horizontal stabilizer trim actuator, which then is mechanically linked to the stabilizer. Alternate pitch trim switches are inhibited when the autopilot is engaged. Pitch trim does not move the control column. In the normal mode, alternate pitch trim operates differently on the ground than it does in flight. On the ground, using the alternate pitch trim switches will move the stabilizer directly. In flight, using the alternate pitch trim switches commands the PFCs to change the trim reference speed. In the secondary or direct modes, alternate pitch trim operates the same on the ground and in flight. In both situations, the alternate pitch trim switches will directly position the stabilizer. The pitch envelope protection functions include overspeed protection and stall protection. Overspeed protection reduces the likelihood of inadvertently exceeding VMO or MMO by providing enhanced crew awareness of the approach to an overspeed condition. Overspeed protection limits the speed to which the airplane can be trimmed. At VMO or MMO, the trim reference speed is limited by inhibiting trim in the nose-down direction. The pilot must apply continuous forward column pressure at twice the normal force to maintain airspeed above VMO or MMO. Stall protection reduces the likelihood of inadvertently exceeding the stall angle of attack by providing enhanced crew awareness of the approach to a stall or to a stalled condition. Stall protection limits the speed to which the airplane can be trimmed. At approximately the minimum maneuvering speed, the trim reference speed is limited by inhibiting trim in the nose-up direction. The pilot must apply continuous aft column pressure at twice the normal force to maintain airspeed below the minimum maneuvering speed. The PFCs calculate field commands based on airspeed. In general, control column forces increase as airspeed increases for a given column displacement, or as column displacement increases. In secondary and direct modes, the elevator variable field system provides field force levels based on flap position, instead of a continuous variation with airspeed. With the flaps up, the field forces provide maneuver force levels that discourage over-control in the pitch axis at high speeds. With the flaps out of up, the field forces decrease to provide force levels appropriate for approach and landing. During takeoff or landing, the PFCs calculate if a tail strike is imminent. If required, the PFCs decrease elevator deflection to reduce the potential for tail contact with the ground. Activation of tail strike protection does not provide feedback to the control column. If activated, takeoff performance will not be affected. In the normal mode, airplane roll control characteristics are similar to conventional airplanes. Unlike conventional airplanes, the control wheel does not directly position the lateral surfaces in flight. Instead, it commands a roll maneuver with the rate dependent on wheel displacement. Control wheel displacement incorporates artificial control wheel forces, which increase as control displacement increases. These forces do not change with airspeed changes. The flight control system automatically positions the ailerons, flaperons, and spoilers to generate the commanded maneuver. At high speeds, the ailerons are locked out and only flaperons and spoilers are used for roll control. Automatic control surface commands minimize airplane roll response to turbulence. The system will constantly monitor airplane responses to pilot inputs and reposition the lateral surfaces to carry out these commands. Airplane roll control in the secondary and direct flight control modes differs from normal mode. The flight control system continues to receive and process pilot control inputs using simplified computations to generate flight control surface commands. Bank angle protection reduces the likelihood of exceeding the bank angle boundary due to external disturbances, system failures, or inappropriate pilot action. Bank angle protection provides roll control wheel inputs when the airplane bank angle exceeds the bank angle protection boundary of approximately 35 degrees. When the boundary is exceeded, the PFD bank indicator changes color to amber, and the control wheel force rolls the airplane back within 30 degrees of bank. This roll command can be overridden by the pilot. Bank angle protection can also be disabled using the autopilot disengage bar. The roll envelope bank angle protection is not available in the secondary or direct modes. In normal mode, airplane yaw control characteristics are similar to conventional airplanes. Unlike conventional airplanes, the rudder pedals do not directly position the rudder surface in flight. Instead, the pedals command a side-slip maneuver, with the airplane's side-slip angle dependent on pedal displacement. The flight control system will then position the rudder to generate the commanded maneuver. The system constantly monitors airplane response to pilot inputs and repositions the rudder as necessary. Pedal forces increase as pedal displacement increases. These forces do not change with airspeed changes. A rudder ratio changer automatically reduces the side-slip command for a given pedal input as airspeed increases. Sufficient rudder authority is provided at all airspeeds to maintain airplane control in engine failure conditions and during takeoffs and landings in crosswind. Airplane yaw control in the secondary and direct flight control modes differs from normal mode. The flight control system continues to receive and process pilot control inputs using simplified computations to generate flight control surface commands. The rudder pedals command a proportional rudder deflection instead of a maneuver command. Pedal feel forces are unchanged from normal mode, but rudder response is slightly different. In secondary and direct modes, the rudder ratio changer is based on flap position. With flaps up, the rudder response to pedal inputs is less than the response when the flaps are not up. In the secondary and direct modes, gust suppression is inoperative. Asymmetry compensation is inoperative. Flight envelope protection is inoperative. And yaw damping is degraded. Manual rudder trim operation is provided in all three flight control modes by a rudder trim selector located on the aft aisle stand. Two rudder trim rates are available. A low rate is commanded with the selector rotated to the detent, and a high rate is commanded when rotated past the detent. To provide pilot awareness, the pedals move to reflect the amount of manual rudder trim applied. When ground speed exceeds 30 knots during the takeoff roll, manual trim inputs are automatically zeroed, and further manual trim inputs are inhibited until in the air. Manual rudder trim is also inhibited with the autopilot yaw engaged on approach. Automatic rudder trim is provided in the normal flight control mode. To provide pilot awareness, the system automatically moves the rudder pedals to reflect the rudder position being commanded. This trim position is also shown on the rudder trim indicator and flight control synoptic. If the rudder deflection is minimal, the rudder trim remains centered. This prevents running the trim for normal situations, such as to coordinate a turn. On landing, automatic and manual rudder trim inputs are zeroed, so they do not provide a yaw command when the airplane transitions from the air mode to the ground mode. Rudder trim is displayed on ICAS and the flight controls synoptic. The indication on the synoptic is constantly displayed. The ICAS indication is displayed on the ground at power up and after landing if ground speed is less than 40 knots. The indication will also display in the air when any of the following ICAS messages are active: engine fail, left or right; engine shutdown, left or right; engine thrust, left or right; flight control mode; or primary flight computers. The ICAS indication normally blanks when either of the following conditions are satisfied: gear up for 10 seconds, or 60 seconds after liftoff. A digital readout displays rudder position in 0.2 increments from 0 to 1 unit of trim and in 0.5 increments between 1 and 17 units of trim. An L or R is displayed to the left or right of the box for any non-zero rudder trim. A corresponding pointer position is displayed on the line scale below. When the rudder signal is not present or is invalid, the digital readout, left-right indication, and pointer are not displayed. When the rudder trim is inoperative, the digital readout is replaced with an X. Additionally, the box, the X, and the pointer display amber. The pointer will remain on the scale at the last known trim position. The flight control system attempts to maintain a zero yaw rate by automatically adding rudder corrections during reverse thrust asymmetry conditions or takeoffs in crosswind or gusty conditions. Under these conditions, the rudder pedals do not move, allowing the pilot to provide additional inputs to maintain directional control. On the ground above 60 knots ground speed, the flight control system attempts to maintain a yaw rate near zero by commanding rudder to counter the majority of the yawing moment due to an engine failure. The capability to counter a thrust asymmetry is an inherent part of the flight control system. The pilot can still recognize the initial onset of an engine failure through the airplane yaw cue, since the flight controls do not counter all of the yawing moment. Under these conditions, the rudder pedals move, giving feedback to the pilot that the system is working to counter a thrust asymmetry. In flight, when a roll or yaw asymmetry condition exists for any reason, the flight control system attempts to maintain zero roll rate and side slip. An automatic rudder input counters the yawing moment, and an automatic lateral control input counters the rolling moment. Under these conditions, the rudder pedals move to give the pilot awareness of the automatic function. The resulting rudder trim indication is automatically shown on the ICAS display. After the initial inputs, the system offloads any steady-state lateral control input to the rudder, resulting in a small side slip. Since the offload increases side slip on the airplane, the offload has limits based on the severity of the asymmetry. For large asymmetry conditions, a greater side slip is permitted, but some automatic lateral control input may remain after the offload stops. When this occurs, the ICAS caution message roll-yaw asymmetry is displayed. For severe asymmetric conditions, the ICAS caution message roll left-right authority is displayed to inform the crew of the limited roll control available. Automatic lateral and rudder inputs are only available in the normal flight control mode. They can be overridden by manual control wheel or rudder pedal inputs. The wheel-to-rudder cross-tie reduces maximum side slip and vertical fin loads by displacing the rudder in response to control wheel input. This function is available in the secondary and direct modes. In the normal mode, wheel-to-rudder cross-tie is not required. The flight control system automatically controls side slip and fin loads. In the normal mode, the roll and yaw control laws provide turn coordination and Dutch roll damping. The flaps and slats are high-lift devices that increase wing lift and decrease stall speed during takeoff, approach, and landing. The airplane has one inboard and one outboard flap on the trailing edge of each wing, and one inboard and 5 outboard slats on the leading edge. A two-position Kruger flap provides a seal between the inboard slat and the engine nacelle on each wing. In the flaps 1 position, only the slats move. Flaps 5, 10, 15, 17, 18, and 20 are takeoff flap positions. Flaps 25 and 30 are landing flaps positions. Flaps 20 can also be used for some non-normal landing conditions. To protect against inadvertent deployment during cruise, flap and slat extension from the up position is inhibited when speed is more than 260 knots indicated airspeed, or altitude is above approximately 20,000 feet. This protection is only available in primary and secondary flap and slat modes. There are 3 modes of flap and slat operation: primary, secondary, and alternate. In the primary mode, the flaps and slats are controlled together and positioned using center hydraulic system motors. The secondary mode is automatically selected when any of the following conditions occur: the center hydraulic system fails, The control surfaces travel at less than 50% of the normal hydraulic rate. A flap or slat disagree is detected. A flap or slat primary control failure occurs. A primary mode fails to move the flaps or slats to the selected position. Or uncommanded flap or slat motion is detected. In the secondary mode, the flaps and slats are controlled separately and positioned using hydraulic or electric motors. For example, if the slat's hydraulic control fails, the flaps are still driven hydraulically, but the slats are now powered electrically. Flaps and slats are still controlled through the flap lever, but operation in secondary mode is procedurally limited to flaps 20. The alternate mode must be manually selected using the alternate flaps arm switch. Using the alternate flaps arm switch, arms the alternate flap control mode, arms the alternate flaps selector, disables primary and secondary flap-slat mode operation, asymmetry skew and uncommanded motion protection, slat auto gap, and flaps-slat load relief are not available, and disables the flap lever. Once in alternate mode, the 3-position alternate flap selector is used to extend and retract the flaps and slats. Moving the alternate flaps selector to extension causes the flaps and slats to extend simultaneously. Alternate mode flap and slat extension is limited to the slat's middle position and flaps 20. When the alternate flap selector is moved to retraction, the flaps retract before slat retraction begins. Flap position indications are displayed on the primary ICAST display. In primary mode, a single vertical indicator displays combined flap and slat position. The position commanded by the flap lever is also displayed. 10 seconds after all flaps and slats are up, the entire indication is no longer displayed. An expanded flap and slat position indication is displayed automatically when flap-slat control is in the secondary or alternate mode, or any non-normal condition is detected. In the alternate mode, the position commanded by the flap lever is replaced by flap position index marks at all flap and slat positions, and numbers at flaps 5 and flaps 20. The index marks are used as a guide to position the flaps to the desired setting. When the flap lever is in the up detent, all flaps and slats are commanded to the retracted position. Moving the flap lever aft allows selection of flap detent positions 1, 5, 10, 15, 17, 18, 20, 25, and 30. The flaps and slats sequence so that the slats extend first and retract last. Starting from flaps up, selection of flaps 1 commands the slats to move to the middle position. The flaps remain retracted. Selection of the flaps 5, 10, 15, 17, 18, and 20 positions commands the flaps to move to the position selected. The slats remain in the middle position. Selection of flaps 25 commands the slats to move to the fully extended position. The flaps do not move. Selection of flaps 30 commands the flaps to extend to the primary landing position. During retraction, flap and slat sequencing is reversed. The mechanical gate at the flaps 20 detent prevents inadvertent retraction of the flaps past the go-around flap setting. The mechanical gate at flaps 1 prevents inadvertent retraction of the slats past the middle position. Flap load relief is available only in the primary mode. The flap load relief system protects the flaps from excessive air loads. If flap airspeed placard limits are exceeded with the flaps in the 15 through 30 position, load relief is displayed, and the flaps automatically retract to a safe position appropriate to the airspeed. Load relief retraction is limited to flaps 5. When airspeed is reduced, the flaps automatically re-extend as airspeed allows. Re-extension is limited to the commanded flap position. The flap lever does not move during flap load relief operation. Slat load relief is only available in the secondary mode. If airspeed exceeds 240 knots with the slats fully extended, load relief is displayed, and the slats retract to the middle position. When the airspeed is below 225 knots, the slats are driven to their extend position. The slat auto gap function is only available in primary mode when the slats are in the middle position and the airspeed is below 240 knots. At a high angle of attack, auto gap fully extends the slats to increase the wing camber. This will increase lift and the margin to stall. Once the angle of attack decreases, the slats return to the middle position. The auto gap trip threshold is a function of angle of attack, airspeed, and flap position. In the secondary mode, the system is too slow to respond to an auto gap request, so the pre-gap function is used. The slats automatically move to the fully extended position from the middle position when the flap lever is not up and airspeed is less than 240 knots. The slats remain in the extended position until the flap lever is in the up position or airspeed is above 240 knots. Cruise flaps improve the airplane's cruise performance by symmetrically moving the flaps, ailerons, flaperons, and spoilers based on airplane parameters such as weight, airspeed, and altitude. Symmetrically moving the appropriate control surfaces varies the camber of the wing, thereby reducing drag. Control surface movements are minor and no pilot interaction is required. Cruise flaps are only available in the normal mode, above 25,000 feet, and between 0.54 and 0.87 Mach. If the system fails with the flaps in an increased drag condition, the ICAS advisory message, Cruise Flaps System, is displayed. In primary and secondary modes, the flap and slat systems are designed to shut down when a skew condition or asymmetric deployment is detected. When the system is shut down, the corresponding ICAS caution message, flaps drive or slats drive, is displayed. Uncommanded motion is detected when the flaps or slats move away from the commanded position, continue to move after reaching a commanded position, or move in a direction opposite to that commanded. If the flap or slat is operating in the primary mode, uncommanded motion causes an automatic transfer to the secondary mode, and the ICAS caution message flaps primary fail or slats primary fail to display. If motion continues, the system shuts down. and the ICAS caution message "Flaps Drive" or "Slats Drive" is displayed. A disagree is detected when, after a commanded input, the flaps or slats do not move or move too slowly. If the flap or slat is operating in the primary mode and the rate of motion is less than half the normal rate, an automatic transfer to the secondary mode occurs, and the ICAS caution message "Flaps Primary Fail" or "Slats Primary Fail" is displayed. If motion continues at less than half the normal rate, the system shuts down, and the ICAS caution message "Flaps Drive" or "Slats Drive" is displayed. The upper surface of each wing contains 4 sets of spoilers outboard of the flaperons and 3 sets of spoilers inboard of the flaperons. The spoilers are numbered from left to right, 1 through 14. Spoilers on opposing wings are symmetrically paired. Spoiler panels are used in flight and on the ground as speed brakes to increase drag and reduce lift. The spoilers also supplement roll control in response to control wheel commands. All 3 hydraulic systems supply 5 pairs of spoilers. Each hydraulic system is dedicated to a different set of spoiler pairs to provide isolation and maintain symmetric operation in the event of hydraulic system failure. The remaining 2 spoiler pairs are individually powered by 2 electrical buses. The ICAS advisory message "Spoilers" will display when 2 spoiler panels fail in the air, or 1 not down and locked spoiler panel fails on the ground. If 3 or more spoiler panels fail, the ICAS advisory message "Spoiler Pairs" will display. The speed brake spoilers are controlled by the speed brake lever located on the control stand. The speed brake lever has 3 marked positions: down, armed, and up. The speed brake lever can be placed in intermediate positions between armed and up. In the armed position, the spoilers extend and the speed brake lever is driven aft to the up position on landing when the main gear trucks untilt and both thrust levers are not in the takeoff range. When the speed brake lever is not in the armed position, the spoilers still automatically extend and the speed brake lever is driven to the up position when on the ground with ground speed above 85 knots and either thrust lever was previously in the takeoff range before both thrust levers are moved to the idle range, or on the ground and both thrust reverse levers are moved to the reverse idle detent. The spoilers automatically retract and the speed brake lever is driven forward to the down position when on the ground and either thrust lever is moved to the takeoff range, on the ground and there is a transition to in the air, or in the air and either thrust lever is beyond 90% full travel. The auto-drag function operates by deflecting the ailerons downward and raising the 2 most outboard spoilers while maintaining airspeed. Auto-drag is used to assist in glide slope glide path capture when the airplane is above the vertical path. Auto-drag only functions when, in the landing configuration, flaps are at 25 or 30, and thrust levers are at idle. Below 500 feet AGL, the auto-drag surface deflection is gradually removed so flare and touchdown are not affected. This function is active during automatic or manual approaches.